So if you're working on Lab 5, there were a couple things that we did not get to touch on this week in class. So I thought I would make a quick video for you to review these items. So the first thing that we did not get to take a look at is a polyatomic ion. Now, if you take a look at that name, polyatomic ion, it's exactly what it says it is. It has many atoms, and the atoms are bonded together, covalently bonded, and they have a charge. So for whatever reason is they've bonded together, and we can draw some Lewis structures for these, they do have a charge. And so this is known as a polyatomic ion. So here's two examples. You can see the Lewis structures for hydroxide is a polyatomic ion, has an overall charge of -1. Carbonate, you can see there, trigonal planar, a shape, and also has an overall charge of -2. So those are two examples of polyatomic ions. There is a chart of these in your textbook in 4.3, just so you know. All right, so here's 4 important polyatomic ions that you probably just want to know, write down, take a picture of something. Ammonium, which is a positive ion. So if we're writing that in an ionic compound, it's going to come first because it's the positive ion. It's a little different than ammonia, so don't confuse them. And there should have been a couple of more. So hopefully they will pop up later on. Polyatomic ions do follow the cross rule. So for example, if we had lithium carbonate, we're going to write this formula the exact same way we've written other formulas. We're going to look at what's the charge of lithium. Obviously, it's a group 1 metal, so it has a +1. Carbonate, I just mentioned earlier, CO3, 2-. And you simply use the cross rule. And you don't need a 1 there by carbonate. And because you only have one carbonate, that carbonate can be in parentheses, as shown here, or it doesn't have to be. All right, if you have more than one of them, then it needs to be put into parentheses. So let's take a look at aluminum sulfate. So aluminum, of course, is our metal, the positive ion. That's why it's first. Take a look at your periodic table. What's the charge of aluminum? So if you were thinking Al3+, you're exactly right. Sulfate is SO4 2-. Now, on tests and quizzes, you'll be given these. It'll say sulfate, SO4 2-. Those polyatomic ions, I like to think of them as carved in stone. You cannot change anything about them. It's SO4, always SO4. It's 2-, always 2-. All right, and so if we use the cross rule here, what would the formula be? So if you're thinking Al2SO43, you are exactly right. So let's try some examples. Here's a formula for a compound with polyatomic ion. So if you're thinking sodium, and this is actually going to be sulfite, it's SO3, and it's got a 2- charge, but it's not a super important one you need to know. Potassium perchlorate. So that would be KClO4. ClO4 has a -1 charge. Perchlorate. So this polyatomic ion, HPO4, obviously has a 2- charge because I can take that 2 that's down there by sodium and track it back over. So sodium hydrogen phosphate. I'm not giving you, there's not a lot of good ones here. I'll make sure that we look at some more in our next class. So dihydrogen phosphate obviously has a -1 charge. Hydrogen carbonate, obviously a -1 charge, and that's why it's BaHCO3 2, because Ba has a 2+ charge. And you can see my things are a little bit off. There's calcium bromate. All right. And so that's what I have for you regarding polyatomic ions. So I wanted to make sure that I mentioned those to you, especially if you're seeing those in the lab. Number 5. All right, so let's talk a little bit about chemical reactions. And I apologize because it's a little bit off. It doesn't seem like it will adjust. No. All right. So chemical reactions are what happens, of course, when a chemical change happens. And you all have been working for a few weeks now on identifying chemical changes compared to physical changes. And what happens is we take these things that we start with, we call them reactants, and they form products. And we represent this with an equation. So an equation is just our chemical shorthand way of writing them. And you're looking at those in the lab this week. Reactants form products. And we write that with an arrow like that. We can say reactants form products or reactants yield products. And this week in the lab, and I'll touch on some of the different reactions and the reaction types, but you're really kind of taking a look at those this week in the lab. But here they are right here, basically the different kinds of reactions. And I thought this was just a really cool, simple picture that would allow you to see kind of what's going on. And you're going to be looking at these different reactions. And then the important thing you're going to do is because in chemistry, chemistry obviously follows the law of conservation of matter. It's one of the fundamental laws of the universe that matter can't be created or destroyed. We have to balance the equations. And so if we take a look at an equation, like here's an equation, and we'll practice writing more this week, you have to be able to balance it. And so what I do when I am balancing them is I make like a little accounting sheet. So I do something like this, just like I'm doing my checkbook. Money in, money out. So that would be like reactants. Here's our reactants right up here. These are what we're starting with. And this is our product. We have one single product. And if you take a look back at the reaction types, a reaction type when you have one single product is synthesis or combination. So we're combining multiple things to make one product or synthesizing one product. And so what I typically do is after I make my counting sheet, I look at how many hydrogen or how many of each atom I have in the equation. So if you take a look here, hydrogen, I've got 2 hydrogens. So that's good. Then I look on the right, how many hydrogens? Also 2. So that's balanced. Then I'm going to look at my next one, and oxygen, I typically do last. I see I've got 2 oxygens. And here I've only got 1 oxygen. So I would start thinking, okay, so what am I going to multiply that 1 by to get 2? Obviously 2. So I'm going to multiply this by 2. This 2 is then going to go right here. That 2 is called a coefficient, and it's going to go right there. It's what we use to balance equations. But as I've done that, I've also changed the number of hydrogens because I've multiplied it by 2. So now I have 4 hydrogens. So now I got to think, okay, well, what am I going to do to this other hydrogen? I need to multiply it by 2 as well so that I have 4 hydrogens on each side and 2 oxygens. And so that 2 will go right here. And now our equation is balanced. We have 2 hydrogens on the reactant side, 2 hydrogens on the product side, 4 hydrogens on the reactant side, 4 hydrogens on the product side, 2 oxygens on the reactant side, and 2 oxygens on the product side. Now, as I was doing that, it's really just trial and error. I didn't really have a plan for how I was going to do that, other than I was just going to try to account for what's where. So let's take a look at another one. All right, so for this one, again, this is another synthesis reaction or combination because we have one product. And I can see here I have a polyatomic ion. That's the polyatomic ion hydroxide. And so I'm going to start taking a look. I'm going to do inventory. Now, as I mentioned earlier, I like to do the oxygens last, but I can see on each side of the equation, I have Mg, I have H, and I have O. And sometimes if I have a little more complicated reaction, I like to list all the chemical species, is what we would call those first. So I can see I've got 1 Mg, 1 Mg. We're good. Hydrogens, I've got 2 hydrogens. Now this one's a little tricky because this 2 is going to be distributed to both of these elements in here. So that's going to mean I have 2 hydrogens. Now if I take a look at my oxygens, I have 1 plus 1 oxygen, because MgO, that's 1. H2O, that's 1. So that's going to be 2. And here I've got 2 oxygens also. So this equation is balanced as written. I don't need to add any coefficients to this equation. Let's take a look at one more. So this next equation, a double replacement equation, I can tell that because there's 2 compounds as reactants and 2 different compounds as products. And this equation, I picked it because it also includes a polyatomic ion nitrate. You can see I already have it circled there for you. And the great thing about this equation with this nitrate is the nitrate on the reactants stays together to form the product. So I can balance it like that. And so I've listed my chemical species. I've got 4 of each. And as I'm starting to take a look at that, should have 2 nitrates as reactants because this is lead 2+. So that's obviously where that 2 came from. So that helps me to kind of remember that. And I only have one nitrate as a product here. So I need to think, okay, what am I going to multiply this by? I'm going to multiply this by 2. So that will give me 2 nitrates as products, because when I put that big 2, that coefficient, it's going to apply to everything else behind it. So that's important to know. Now I can see that I've got 1K as reactants, and now I have 2 as products. So again, I'm going to multiply this by 2. That 2 is going to be my coefficient here. And now I have 2 Ks, but I also have 2 Is. And if I take a look on my product side, I also have 2 Is. And so now I'm just going to kind of double check everything to make sure that I have everything balanced. Let's see, 1 PB on the left, 1 on the right. So my PB is balanced. 2 nitrates on the left, 2 on the right. So we're good there. 2 Ks on the left, 2 Ks on the right. 2 Is on the left, 2 Is on the right, and so we're all good and balanced. And this just takes practice. If you have any questions, just let me know. I hope this helps you.